Yeah, all good.
Okay, great.
Yeah, thank you.
Uh, yeah, hi everyone. It's very nice to be here. So I'm Badr Al-Khamisi. I'm a PhD student at EPFL. I'm part of the NLP and the Neuro AI labs. Advised by Antoine Bousselou and Martin Schimp, respectively. So today I'm going to be talking about a recent preprint of ours, which we just released recently, called Mixture of Cognitive Reasoners, Modular Reasoning with Brain-like Specialization. So this is a mixture of how we can leverage inspiration from the brain and neuroscience to inform AI design decisions, and specifically how we can modify the architecture to make it more similar to the brain. If you have any questions or if you feel like anything is not clear, please feel free to interrupt me and ask any questions. I prefer to make this interactive. And yeah, let's start. Okay, so the outline for today, we're first gonna do some preliminaries. So I'm sure you all know what large language models are, but I'm just gonna be brief. Also, I'm gonna touch on mixture of experts, so you have an idea how we are extending this to a mixture of cognitive reasoners, and give some neuroscience background in terms of what are the brain principles that we are deriving our design decisions from. Then I'm gonna go over the paper with some experimental setups and so on and results. And then at the end, if we have some time, I'll dive into the code to show you how you can implement such an architecture in the first place. Okay, so let's start with the LLMs. I'm sure you all know ChatGPT and LLMs in general. So before ChatGPT, there was a model called GPT-3. GPT-3 was trained normally using next token prediction. So given a prompt, like the input prompt shown above, recite the first law of robotics, the model generates token by token the output, and it's trained by predicting the next token given a very massive corpus of text. So as I said here, you can basically have a transformer model, which we're gonna go say the details about it in a bit. But let's say you have some parameters and you do this unsupervised pre-training or self-supervised pre-training to be more specific, where you predict the next token, and then you have this model which with all the parameters tuned to be able to predict next token given any prompt you can imagine. So the transformer architecture, or at least the GPT-3 model, was made of a stack of transformer decoder layers. So here we have 96 decoders, and each token is represented as an embedding, so some vector of numbers. And the idea is that each transformer decoder transforms the vector into some more abstract vector, such that it can capture the concept of the word rather than just the surface features of the word. And the idea here that after a stack of transformer decoders, it is able to gather enough information to be able to predict the next token properly. And of course, it predicts it step by step, or token by token. So as you can see here, we have the normal, basically autoregressive architecture of a transformer. I can see like there messages on the.
Yeah, I can probably read them to you.
Yeah, maybe if there are any questions, please interrupt me and read them to me.
Yeah, so people ask why there is no encoder here or why only decoder is used.
Yeah, that is a good question. So GPT-3 and more modern architectures, they only use a decoder architecture, so they don't use an encoder with it. So examples of encoder-decoder models are like T5 or BART. An example of an encoder-only model is BERT, but all modern architectures, they only use decoder-only models. By that, that means that it is causal. So it only predicts the future tokens only attends to previous tokens, and they cannot attend to future tokens. And this is the reason that people abandon kind of encoder models is it scales better. Like decoder only model scales much better, and you can scale it to billions of parameters or even more, and it works well. Okay, so this is a quick recap of what LLMs currently do from a very high level sense. And if you go a bit deeper, like if we open each decoder layer, we will see something like this. So usually we have the tokens uh, is passed as input. This is normalized through a layer norm layer, and then you have the multi-head attention. The multi-head attention is basically the mechanism that attends to previous tokens in the sequence. So it kind of like weights each token such that it knows which one is the best token for it to gather information from to be able to predict the next token. And then we have those residual connections. Actually, can you see my mouse pointer or?
Yes.
Okay, great. So we have those residual connections. It's kind of like a highway that allows information to bypass certain layers. And then this MLP, which is we're gonna talk about in detail now. The MLP is mostly like a token-wise MLP, so it doesn't process sequences, it processes each token on its own. And this block, or let's call it transform block, is stacked multiple times on top of each other to be able to do this layers of abstraction I was talking about earlier. And a mixture of experts architecture is, I mean, basically what they do, they change the MLP to a mixture of experts layer. So as you can see, it's exactly the same architecture. The only difference is we have a difference in the MLP. So what is it exactly in the MLP? It's actually a bunch of MLPs. So what we do is we have this input token that's output of the layer norm is given to the MOE layer, and this is passed to a router. The router then decides which MLP or which expert it needs to route to. Also note that the MLP is usually sometimes called feed-forward network or feed-forward layer. But yeah, I mean, it's exactly the same thing. And what
Sorry,
happens in, yeah,
what
go
is the
ahead.
difference between layer norm and batch norm?
People are asking what is layer norm. Layer norm is, you can consider it as a way to normalize the values of the vector that the tokens are, because each token is just a vector of numbers. And we want to normalize those across the layer instead of across a batch, across the layers and across the hidden dimension. And this is usually done to be able to make the training more stable and is pretty, yeah, it allows training to be able to converge more quickly as well.
Okay, it's clear. Thank you.
Okay, cool. Yeah, I hope the mixture of experts idea is clear because this is pretty important. What we do is, again, like we have different MLPs. Each MLP is kind of like an expert. So we can have something like, let's say, a medical expert, a math expert, uh, I don't know, physics expert, and so on. And the router should learn which token, which expert is best for this token, or which bunch of experts, because like you can choose more than one expert actually. And then this is weighted together to the on top and passed to the next layer afterwards. Yeah, so here in this case, we only like in this example, we only choose the top two experts, and we ignore all other experts. So one thing you might have noticed that we don't use all parameters in this case. So sometimes if we have like 8 experts, we only use 2 of them. So this means that the number of parameters in the model is much less than the number of active parameters. So active parameters in this case are the parameters that are used during a forward pass. And in general here, if we're using, if you have 8 MLPs, then the parameter size will be much bigger than the normal transformer, like a dense transformer. But at the same time, we're using less, we're not using less parameters, but we're using less than the total number of existing parameters in the model. And the router, what it does, it has a softmax layer. So it outputs a probability distribution over the different experts. So if we have 4 experts, it's going to have 4 values, like from 0 to 1. And those values are then weighted with the experts that are that are chosen for this token. And to give you an example of a mixture of experts model, so Meta or Facebook, they released a model called Llama 4, if you're familiar with it. Llama 4, if you notice on their website, it's actually a mixture of experts model. So you can see, like, for example, the Llama 4 Behemoth, I don't know how to pronounce it, but like it has 16 experts for every layer and has a total of 2 trillion parameters, but only 288 billion active parameters, and so on. So the Llama Maverick is like 128 experts and 17 billion active parameters. So in general, the active parameters is the thing you care about, because it kind of equates to the number of the amount of compute you need. And the amount of compute is like the amount of money you need to run this model on a server or something. There's another question.
Sorry, how the router is choose the MLP?
How the router? So the router learns to. I mean, you don't in a normal mixture of experts, you don't have specific. You don't know you don't specify the expertise a priori. So you kind of allow the model to learn the expertise on its own, and then you can analyze this, what each MLP learned post hoc. So in general, the router would, for example, like given a token, it will decide to route token number, like the token to expert 1 and expert 5, let's say, and then given enough tokens to those 2 experts, they kind of converge into a specific expertise, because they're only given a specific type of tokens, and different types of tokens are routed to another set of experts. And in general, like in practice, there's something called a load balancing loss that allows the router to not only choose 2 experts out of like the 128, for example, but it allows it to make sure that all experts are being used. If that makes sense.
Yes,
Not
thank
sure.
you.
May I ask, as far as
Yeah.
I understand, we apply softmax function to the outputs of the models.
Yes.
But if we use it to choose the MLPs that should be applied to the certain token, shouldn't we pass the token through all MLPs to decide which expert to use?
No.
So-
So
Okay.
yeah, I see your point. So in general, no, the token is passed to only the MLPs that the router chooses. So the router, like, that's after training, not during training, like during inference. The MLP, the router, each token is passed to the router, so all tokens are passed to the router. But the router will decide that for this token, it's going to go to expert 1 and expert 5. So it's only going to go to those experts, and then we're going to reweight the softmax such that it gives like 80% weight to x first 5 and 20% weight to x first 1, for example.
So router acts like some other model in this case.
The router itself is an NLP actually, usually, or a linear layer that projects to, like, if you have 4 experts, it's gonna project to like just 4 values, which we're gonna do a softmax on top of it.
Okay, thank you.
So the router training to choose MLP, to choose the expert, yes?
Sorry, can you repeat that?
The router is training to choose experts, yes?
Yes, exactly. The router is trying to choose the expert, yes. Okay. Cool. Well, I hope that was clear. I mean, I didn't go into the details here because the way I implemented it in my paper is a bit different. So, but in general, this just gives you a high-level idea of how it differs. The mixture of experts architecture differs from a normal transformer layer. Okay, so we did say that there's like state-of-the-art mixture of experts model out there. Llama 4 is one example. There's other examples as well. Many people hypothesize that ChatGPT is a mixture of experts model. I mean, it is, I think, I mean, it's not announced or anything officially, but that probably is the case. And yeah, it's kind of like a new, not a new method, but it's becoming the way of building very large language models. Okay, another question. The question is asking, is there not a danger that some experts will become neglected during training? Yes, so this is what I was saying about the load balancing loss. You do add something like another loss to the cross entropy, which basically penalizes, as you say, to be able to use all experts more or less throughout training. There are different ways of implementing this, but in general, you can think about it as yeah, penalizing if you only choose a few experts over like all of the experts in the model. No, the router is a couple of connected linear layers or just an MLP basically. And sometimes it's only a linear layer in many cases. Okay. So I'm gonna move to some neuroscience background to talk about the brain inspiration. Okay, so in the brain we have some set of let's say call them cognitive networks. One of them is something called the human language network, which neuroscientists have identified and studied for many years. And those are usually a set of interconnected regions in the left hemisphere primarily, and they respond robustly to linguistic input over non-linguistic input. And they have a lot of properties which people have studied, but the main idea is they process language and from morphemes to basically the phrase level. So different levels of the hierarchy, more or less. And as I said, um, if you measure activity of a person when he's speaking or listening to language, those areas are going to be the most active. And again, if you plot on the like here on the y-axis, we have how active the language regions are compared to different inputs. So if for linguistic input, regardless of whether it is like people are listening or reading to text, they have much higher activity than non-linguistic input, like music, like listening to music, for example, or some object semantics, hand and body perception, or theory of mind. So those are all like different ways that people perceive stuff, and those areas in the brain do not light up when you listen to those stuff. And we have as well other networks in the brain. So one of them is called the multiple demand network. which mostly handles like formal reasoning, so logical, physical reasoning, and so on. It's called multiple demand because it usually handles demanding tasks. And then we have something called the theory of mind network. This is mostly responsible for social reasoning, pragmatics, being able to infer other people's mental states, and so on. And there's another network called the default mode network, which is kind of like responsible for situation tracking, so tracking entities and the relationships across time. And those networks. There's much more and much more, let's say, functionally specific networks in the brain. But in general, I just chose those because they have been studied in the literature. And as you can see, there are some parallels here with the mixture of experts architecture, because this functional specialization in the brain, or this modularity, kind of lends itself to an idea of being able to model it using some different experts in the model. And this is exactly what inspired the idea of building the model I'm going to talk about now. Okay, so in terms of machine learning terminology, let's say, I kind of renamed those networks into a logic expert for the multiple demand network, a social expert for the theory of mind, and a word expert for the default mode network. And as well, we're going to have something called the language expert, which is analogous to the language network in the brain. Okay, so this brings us to the start of the paper, a mixture of cognitive reasoners. If you have any questions, feel free to ask before I move on about the previous sections. Okay, then yeah. So a mixture of cognitive reasoners was done in collaboration with people at TPFL, Nicolo De Sabata, Zining Shen, and under the supervision of Martin Schermpf and Antoine Bosselot. And the main idea is we have those different experts, and here I'm gonna basically just say what kind of knowledge the experts should be good at, or should be able to process, basically. So the language expert, as you can imagine, is responsible for linguistic patterns, grammatical structure, vocab usage, syntax and semantics, among others. The logic expert is like logical reasoning, mathematical reasoning, physical reasoning, computer code comprehension. Those are all like different stuff that people have measured in those brain areas. So people have measured, like, for example, the brain activity of people reading computer code, and they saw that the multiple demand network, or the logic expert in this case, usually lights up much more than other areas in the brain. And the social expert, as I said, is emotion states, theory of mind, pragmatics such as irony, sarcasm, and deceit, as well as social interactions, like very subtle cues in social interactions. You have these areas in the brain like kind of firing up. And then the word expert is word knowledge, spatial and temporal reasoning, world building, cause and effect. Like those are all different properties that people have shown in neuroscience that those networks are kind of responsible for. And again, this is what we model in the mixture of cognitive reasoners. So taken together, we have those different brain networks, and each brain network corresponds to some expert in the model. And the main architecture here is we have, I mean, this is a very compact version, but as you can see, you have like the 4 experts. But here, instead of one major decision we did was we changed the experts. Instead of having only an MLP, it's actually a full transformer layer. So it includes the attention as well. So each expert is an attention and an MLP. And yeah, the router then decides which expert it needs to route to. And this is stacked L times on top of each other. And this then, once it's trained, it allows us to steer the behavior of the model. So given a prompt, let's say we only activate the social expert alone, and we don't activate any other expert, we kind of get like more of a social response. If we activate only the logic expert, we get like the prompt here is like, Dennis invited 6 of her friends to her birthday party, but is worried that most of them will not come, what should she do? And the logic expert kind of like breaks it down step by step and like answers very logically. The word expert kind of like repeats, like basically restates what that question says. The language gives a more general response, and etc. And I'm going to show more examples later on. But this is the basic idea, and I think there is a question.
Sorry, but if we use only two experts, but our will be depends on three behaviors. How this model will be work?
Okay, sorry, can you say that again? I didn't get the question. Can you repeat the question? Sorry.
Okay. Sorry. You said that we choose only top two experts, but if our prompt will be using social logic and world behavior, how our model will be use three experts if we take only two best?
Yeah, so in my case, actually, I chose the top one expert, even not top two. And the reason is I wanted to keep the number of active parameters to be the same as a model without any experts, to be able to make it comparable. But the main idea that the model has several layers, right? So this is what I'm going to show next, actually. Yeah, like for inducing specialization. So the model is actually like many layers on top of each other, and each layer has a router. So each layer, you kind of can decide on a different expert. Like for example, the first layer, you're going to choose a language expert. The second layer, there might be more logic. Third layer might be, I don't know, something else, and so on. So kind of you have like different experts, and you have this for every token in the sequence. So every token in the sequence, you decide on which expert you need to route to. So here you kind of make use of all the experts in very different ways, if that makes sense.
Okay, it's clear. And one more question: how our model will learn which expert will be language, or which expert will be logic, or which expert will be social? How our model is learned?
Yeah, exactly. That's what I'm going to talk about now. So this is where about inducing specialization, and inducing specialization is the way we kind of make the training. We have a training curriculum that allows each expert to specialize at the beginning, and then we train it end to end. So here I'm giving an example on the left. Like we have some data set that we created that such as like this one, like has May baked 9 cookies for 3 friends, but one couldn't come. How many cookies per friend? How many cookies per friend now, and what should May say? So I mean, this is anyway a random question, and then the model responded. She can give 4.5 cookies to each of the 2 friends. She might feel a bit disappointed. She could say something, and then etc. And the main idea here that each part of the response is labeled to go to one expert. So, and we do this labeling with the way I'm going to discuss next. But in general, the main idea that we have a very small data set that is labeled this way. And this is what we train using for stage 1. So we have different stages for training the model. This is stage 1 where we only train the experts on only the tokens that is labeled to go there. And then for stage 2, we only train the router. So the main idea here that we give a little nudge to the experts at stage 1, and at stage 2, we tell the router, or we allow the router to learn to route to the expert that kind of chooses which expert is best to predict the next token. So if the logic experts have seen many mathematical stuff, for example, so it makes sense for the router to route to it anything that needs math to be able to predict the right answer at the end. And in stage 3, we actually unfreeze everything. So everything is trainable, and we train it end to end. And we don't, and we don't specify anything. It's just like the router is allowed to be routed to anywhere. decides to, and it doesn't need to be. I mean, there's no labels here. It's just self-supervised training. And there is a question. Can see it now.
I can read it.
Yeah.
So at stage 1, we have the tokens labeled to which experts they need to go.
Yes, exactly. I mean, not on the token level, but at the phrase level. So here, for example, at each sentence in the response, we kind of labeled this token should go to that expert, exactly. And this is what I'm going to discuss next, like how we created this data set.
Uh, Actually, to build on top of this question. So as far as I understood your idea, like I see two options. First one, you only use, for example, green models, green MLPs, and your input is only about language. Your prompt is only about language. Then you use only blue models, and your input is only about logic. And you train on such input-output context. Or the second approach, you split your input sequence into different categories, and on each layer of your decoder, you like look at this label, let's say like whether it's a language part of a token or logic part of a token, and give it to the corresponding expert. So which of these are you doing?
Yeah, it's the second one. So we have the input sequence, each token kind of labeled which expert should go to. And therefore, like if you have, let's say, if you have the first token, the token goes to the logic expert, and the tokens before it went to the language. So token 2 will attend to the language, the output of the language expert, because this is the previous one. So kind of this way, it kind of interleaved this way, because different tokens in the sequence go to different experts.
So when we calculate attention, do we mix information from different parts of tokens, like from different categories? Or we calculate attention only between language tokens, only between logic tokens, or only between social tokens?
Yeah, so exactly. So that's where the method I did here differs from a normal mixture of experts. A normal mixture of experts, you have a shared attention between all tokens. The way I did here, I have a attention specific to each expert. But the thing is, because the next layer takes the output of all, like the sequence in the layer 2, the input sequence will have output of different experts. So this is how it's kind of like is interleaved together. I think it's going to be clear later on exactly.
And just one more question.
Yeah.
So before you showed that, for example, logic expert is about math reasoning, physics reasoning, and code reasoning. But we treat logic expert as one MLP, or with another moire where inside you have another router, one for math reasoning, one for code reasoning, one for...
Yeah, that's a good question. No, it's just one transformer layer. So it has an attention and then one MLP alone.
Got it.
It's not. Yeah, it's not like it's not a hierarchical mixture of experts, if that's what you're asking.
Got it. Thank you. And maybe the last one. So the whole idea of these experts is to improve interpretation of your network. Like for original Moye, I guess it was more about making it wider. But here you do not care about making it wider and giving more expert, you just want interpretability.
There are a couple of things which I'm going to discuss later, but the main idea, yes, is interpretability is a major thing. As well as we're going to see, is actually, even though we have almost the same number of active parameters, it kind of improved the performance on some benchmarks. And other than that, it kind of allows it to be able to compare some stuff to what's happening in the brain in terms of behavior, in terms of which network is active, or compared to when you're given some input and stuff like that. But yeah, this will be clear later on.
Yes, thank you.
Sir, last question, I think. When we get a prompt, how we get a pseudo-labeled response? after prompt.
How do you get what, sorry?
How we get pseudo-labeled response from prompt?
I guess how you define the category for this prompt.
Yes, yes.
Like a category as like for the stage one when it's labeled, do you mean?
Yes.
For the-
Yes.
Yeah, so yeah, okay, so yeah, this is a good segue to the next part, which is the data creation. So yeah, the data creation is basically what we did here is we kind of like divided, we use existing data sets and that we kind of like label them from a very high level sense that those data sets belong to logic, those data sets belong to social, those data sets belong to world. And we sampled a very small sample from each, a very small subset from each data set. So we'll have a total kind of like 1,000 samples, almost 1,000 samples per one of those three experts. So those end up with 3,000 samples, which we use to train the stage one part and stage two. So those are very few samples, if you get it. Yeah.
Are there any problems that you have disbalance between math and physics, for example?
No, it's kind of arbitrary. Yeah, I mean, I would like if going back, like if I go back in time, I would have chosen those much more carefully. But I kind of like I did it this way, and it kind of worked. So yeah, I kind of continued from there.
Nice, thank you.
Yeah, and so this is like the first step of the how we created the data set. The second step is actually we use O1 to generate a response. So this is like the prompt here is from one of the emotion, some data set, I forgot which one. And then O1 responds like a very long chain of thought reasoning response with a very like step-by-step answer. And then this idea is we then use the input, which is the prompt, and the output, which is the response, as the input to the model during the expert training phase. And the way we labeled it is we used GPT-4o to label each phrase to one of the four experts. So basically all that is automated. We just did the prompt to GPT-4, GPT-4o, and to O1 to be able to just give it the knowledge of how to pseudo-label each phrase. But then we'll have something like this where we have a prompt, and then we'll have each phrase or sentence in the prompt labeled to some expert, basically. And if you don't know, like what is O1, for example, I'm sure you probably all know, but like O1 is one of the reasoning models of OpenAI. And the reason we use it at the because it was the one available at the time. Now there is like O3, and I'm not sure if O4 is out, but yeah. Okay, cool. And then for stage 3, which is the main training, we chose a large-scale instruction tuning dataset, which is called Tulu-3, and this contains almost a million samples, so a million input-output pairs, and covers a wide range of domains, as you can see here, like on the right, like from multilingual stuff to algebra, Python, yeah, very general stuff like that. And in this stage, we don't specify which expert, which expert the token should be routed to. The router kind of like figures that out by itself. So in some scenario, like it could have decided to remove the specialization it learned at the beginning and learn a new specialization. But that didn't happen, and that we take that as evidence that the specialization we did at the beginning is actually good enough for the model to be able to solve those tasks. Okay.
Sorry, there was another question. Could you
Yeah.
please repeat how again you did the labeling of your data for the small data set where you prompted, where you generated prompts? Yeah,
Yes.
this part.
Yeah, so we decide. So we have an input. So from those data sets that we collected at the beginning, we collected those manually, and then we decided to take the input part only. So let's say the user prompt or the question, and generated the response using another model, which is O1. O1 usually generates a very long reasoning chain from the response. And then we told, given this response, we told a model like GPT-4o some criteria, how to label each phrase. And it kind of generated for us a big JSON with each phrase corresponding to which expert. After like our long instruction, the instruction is in the paper, in the appendix, so you can see it, but in general, that's the main idea.
People ask if the quality of the model used critical to the performance of the approach.
Yeah, that's a good question. No, we did control for this, and I'm gonna show it in the results. But
Thank
yeah,
you.
I mean, definitely, yeah, I mean, let's wait until the results. Okay. Okay, so yeah, so some results is the first thing is the interpretability part. So if we took a benchmark such as math, we can see that most tokens, so this is like the percentage of tokens routed to each expert. So a benchmark like math will route most tokens to the logic expert, a little less to the language, and a little less to the word, and none to the social. So this is kind of like evidence that the model works as expected. And for other benchmarks, there's some benchmark called the empathy benchmark. I guess you can ask a question like, what do you think would be the most routed expert? Do you have any idea? You can just write it in the chat maybe, or something. Okay, so somebody says social language. Yeah, I mean, so it's actually social and then language, which is a very good guess. We won almost none of logic, and then the world expert a bit for, I guess, some situation tracking and whatnot. And then we have MMLU humanities. MMLU humanities is routed to the world expert and the language the most, and logic and social much less. GSMAK is like high school, not high school, like it's math word problems basically. So it contains some of math, some also you need to track characters and so on. So you have logic and language at the most, and then the world one as well. So those are just some examples, but just to say that the routing patterns are interpretable to us and make sense. So we can have like any input to the model, we kind of know which expert is routed to. Somebody's asking what is MMLU. MMLU is a very famous benchmark in machine learning. It's about word knowledge almost, like asking something about some history questions and like it's factual questions mostly, I would say. And it contains many different subtasks or subsets belonging to different categories. I think the name is massively multitask language understanding benchmark. Okay, so this is for the routing patterns. We also analyze it per layer, and for example, for one very interesting thing that happened, which personally I wasn't expecting it at all, is this thing that at early layers you can see that the language expert is much more used than later layers, which kind of makes sense, right? Because like in the brain as well, like usually you have an input, you perceive like some sentence or something. This is usually passed through the language network first and then passed through those higher level cognitive networks. And we see this, that the model learned this on its own without us specifying anything. And the kind of like we have we have on the x-axis the layer number, and here we have the percentage of tokens routed to that expert. So as you can see, language is much more at the beginning, and you have the other ones later on, emerging later on. And again, like this is some example of which token is routed to which expert if you took a majority vote across layers. And as you can see, for example, we have the blue part here is like an equation. Is 5 minus 2 equal 3 is like routed to the logic one. You have the word surprise and disappointment routed to the social one, etc. So it's kind of like all of this is kind of evidence that those patterns make sense. Okay, so
Sorry.
yeah.
About previous slide, why A and D are so different? Like the data sets should be similar. No, D is also about math, as far as I remember.
Yeah, but A is more of like it only includes like it's kind of like LaTeX style math, right? Like it has a lot of LaTeX equations, it has a lot of formulas and stuff which don't include language as much. If you see GSMAK is like I don't know, John bought 8 apples, he sold 3 and ate 2. Each apple is like $5. How many? I don't know. What's the how much profit did he make at the end? Something like that, right? So this kind of includes language much more, and includes as well being able to track objects and stuff throughout the text, stuff like that. I mean, this is my hypothesis. At least I haven't verified this myself.
Got it. Thank you. And there was an old question. Is it possible to train 4 independent models, like one trained only on logic tokens, one trained only on language tokens, and then somehow combine them, like instead of doing routing and all of this, I guess. Like train 4 models and then combine them.
Yeah, this has been done actually. There's a paper called Mixture of Transformers. I think they do something similar to this. So yeah, this is possible, but we kind of wanted to have some unified model together to be able to do that.
Thank you.
Okay, so performance. So yeah, I mean, one thing I didn't mention is we experimented with 2 base models. So the training curriculum I said at the beginning, we actually take a pre-trained model, so a model that's pre-trained already, and we do supervised fine-tuning or instruction tuning on it. We basically continue training it on 203 and other texts. So we chose 2 models, Olmo 21B and Llama 3.21B. The reason is those are like we chose 1 billion model because it's a reasonable size. It's good enough, and it's also small such that we can iterate a lot on it and do a lot of experiments. Yeah, and they're both good models. And we did some baselines to compare against. So we have our specialized model, which is what I just discussed before. We also have a general model, what's it called general, which is basically during stage 1, we have, instead of having labels to each token, we route each token randomly to a random expert. So this is where I was saying the control part, because this one was trained using O1 as well, but instead of having specific labels for each expert, we kind of like the router is routing randomly to each expert. And then, but this routing randomly is only at stage 1. Like stage 2 and stage 3, the router is trained. And the idea is because there is no, we're not inducing specialization at the beginning, so the router is kind of like, yeah, it should figure it out on itself, which experts it should train, it should route to. And the final baseline is the most basic one, which is we don't have any experts, so this is basically the model itself, continued or fine-tuned on the dataset. So yeah, those are 3 baselines. We have the 2 baselines we have in our model, and the benchmarks we tested on are grade school math, elementary core knowledge, theory of mind, big bench, MMLU, and math. To give like those are kind of some reasoning benchmarks we measured the performance on. One thing to note as well that each benchmark was either measured using zero-shot or few-shot chain of thought prompting. So zero-shot meaning that we didn't give it examples at the beginning in the prompt, and few-shot we usually give it like a few examples in the prompt before asking the question. And chain of thought means that we ask it to provide the reasoning or the explanation before giving the answer at the end. And this usually improves performance more. Is everything clear here? I'm not sure if everyone's familiar with the chain of thought prompting. I mean, you don't have to be familiar with those benchmarks, but yeah, the idea of chain of thought prompting is important, I think.
Sorry.
You should mention it, I guess, because not everyone knows. Like we didn't cover it in the first week, what is chain of thought. So
Yeah. Okay, sounds good. So let's go back to this example. I'm not sure if it's very clear, but for example, here in the question I ask, like, let's think step by step at the end. And let's think step by step is kind of like prompting the model to generate a step-by-step answer until it generate the answer at the end. So it's kind of like the response is like, let's analyze the scenario step by step to determine why Henry responded the way he did. And then it kind of like does step-by-step answers. And this idea of providing a reasoning or the reasoning process before answering the question is kind of like what is called chain of thought usually. And if we have a zero-shot chain of thought, it just means we just tell it think step by step, like that's it. If it's a few-shot chain of thought, we provide reasoning in the prompt as well. So we provide some examples of input-output pairs and the reasoning before the output. So yeah, this is usually helps the model to be able to converge to the right answer in a better way by decoding more tokens, like providing more compute time during inference. If that makes sense.
thank you. Actually, I have one question because maybe
Yeah.
I misunderstood something. Just to be sure. So in traditional MOE, we had our input prompt, like we passed it through encoder, and the whole prompt went to like 1 or 2 MLPs, and we combined the outputs then. In your case, router is not about choosing which expert to use. It's about for each token saying to which router we should pass this token. Am I right or not? So like in your case, we again choose through the router to use only 2 experts, or we use all the experts we have, but some tokens are passed only through language experts, some tokens are passed only through logic experts, etc.
Yeah, so in my case, each token is passed through only 1 expert, and this is chosen by the router. In traditional MOEs, as you said, they choose the top K experts, and then they aggregate the representations of the K experts at the end. In my case, I just take the representation from the expert that the router shows.
Yeah, but so imagine we have like a prompt with 2 tokens, like 2 cats. No, let's say like 4 cats. 4 is a number, so probably for the logic expert, cat is for a language, for example. So we take the full prompt and pass it to, as a whole, to logic expert or to language expert, or we say that the word cat goes to the language expert and the word for goes to the logic expert.
Yeah, we say the router decides that the word for goes to the logic and the word cat goes to the language.
Okay, so we split the sentence into, we split the tokens into groups for each expert. While
Yeah,
in traditional Moye, we didn't split the prompt itself, we just chose which way to go, yeah?
oh, I see your point. I see your question. No, so no, it depends. So there are in traditional MOEs, usually MOEs are done on token level as well. So they route each token to a different expert. But there are other types of MOEs that are done on the sequence level. So they route the whole sequence to a specific expert or specific K experts, let's say. Those are different types, but usually the token level one works better in practice.
Okay, now it's clear. Thank you very much.
Okay, so there are two questions. One is like, can you explain the difference between general model and specialized model? Yeah, so if you remember in the training curriculum, basically general and specialized have exactly the same thing, except at stage one. So they have the same training, the same data set, the same everything. But at stage one, they don't have the labels of each sentence. So they don't have the specialization of the experts. Instead, what happens is each token is routed randomly to a different expert. So we have like, for example, those in this input example, she can give 4.5 cookies to each of the two friends. Instead of routing this to the logic one, we're going to route it to to random experts. And this way, each expert is not an expert in something, but it's a general expert, so to speak. And this is how we control basically for measuring the effect of specialization. Because here we have everything is constant except the labeling part that we did at the beginning. Okay, great. And the second question is zero shot and few shot. Yeah, that is okay, so zero shot is the normal thing, is basically you just ask a question and then you get a response. Few shots you have in the prompt. Like you have in the prompt some demonstrations of the question. So like other questions basically. So you have like, let's call, you have like a bunch of input output pairs. So question and answers. You have Q1A1, Q2A2, Q3A3. So you give in the prompt, you give all of those pairs. So you give the prompt Q1A1 and Q2A2 and Q3A3. Then you give it Q4 and you ask the model to answer Q4 alone. And Q4 is basically the question you're interested in, but the remaining, the first three questions and answers are just examples to show the model that it can, how to answer such a question in the first place. So this is what we call few shot. And if you have three questions, it's called three shots. I hope that's clear. Okay. Cool. Okay, so yeah, we sorted the results. And just to give you an example, an idea, those are the results for the no experts in general for if we're trained on Olmo or trained on Llama. And yeah, no experts in general basically is on average, no expert is a bit better. But yeah, the difference is not that much in many cases. And if we looked at the specialized is better on some benchmarks more than others, but on average, it's usually better by 1%. In general, this is actually, we usually in machine learning, like people, when they say interpretable models, they usually say that they want to sacrifice performance to have interpretability. But here for us, it was a very, very good thing that the model actually is even better, even by a very small margin, but it's better than the other models and is interpretable at the same time. So that was for us a big win. But we also tried other ways of prompting the model. So we have something called specialized star. So specialized star is basically we remove an expert from the model that is not relevant to the benchmark. So let's say for GSMAK, we remove the social one because GSMAK is more like logical. And if we remove the social one, we actually like we see a very big jump in performance to 47.6. So that kind of means that the router routes to some tokens to the social, even though it shouldn't have routed to the social. But removing this kind of boosts the performance much more. And then we have another one that kind of improve performance as well. Is here at test time we chose top 2 instead of only top 1. So this is kind of like increasing test time performance in some sense. Increasing test time compute. And basically by increasing the compute at test time by choosing more experts, the model is able to get more performance, which you don't get in other models usually. So yeah, to show you an example of increasing, like scaling up test time compute. So what that means basically that we trained only using top 1, but during inference, like during testing, we select more experts at test time. So we select the top 2 or top 3 or top 4. And on the x-axis here, we have like if we select only top 1 versus top 2 versus top 3 versus top 4, and the y-axis the performance. And as you can see on different benchmarks, the results are kind of different, but in general, if you select the top 2 at test time, it's much better than selecting top 1 on average. There's a question.
Sorry, can you previous slide return, please? I have a question
Yeah.
about. So why Olmo with specialized have in evoke 60.4 and Llama without specialized only no experts have 60.2 between
Yeah,
Llama
so those
and
are, yeah, so Llama and Olmo are trained very differently, are pre-trained very differently, right? So here we took the pre-trained models, the model that Meta released and the model that AI2 released for Olmo, and we continue training them ourselves. So it's just because the whole the way it was trained kind of made it a bit different, made the results like it's expected to be different for different models basically. Does that answer your question?
yes, yes. And what conclusion? Does specialized is better than general and no experts? What is the result? Specialized helps us or not?
Yeah, so this is something which was very surprising for us and very good that actually specialization, yes, it does help the performance. And it's not only any specialization, it's specialization in this like in this sense, like the way we did it. And it seems like people in general, like when I told people about this project before I started it, like everyone said, oh, the performance will drop a lot, but that wasn't the case, as you can see. So yeah, specialization in this case does help.
Okay, thank you very much.
Somebody's asking, do I have to retrain the model when choosing top 2? Yeah, exactly. So this is why I was saying it's like scaling up test time compute. So we don't retrain the model. We only select the top 2 at inference alone. And it was kind of like a exploratory experiment I was trying, but we did see, as you can see here, that top 2 on many benchmarks increase the performance like at least by a bit. compared to top one. But yes, this is not like if you did retrain, you'll get much better performance. But here we don't retrain and we just try the testing. Somebody's asking how is the score percentage being defined? This is exact match. So basically, if the result, if the performance is exactly, if the answer is exactly the same, then the exact match is 1. Otherwise, if it's not the same, it's going to be 0. So for math, if you have like a very complicated question and then you say like the answer is X, you compare X with X like a string equality, and then that's the accuracy basically of that.
So it's the multiple choice, like so we train with like a number of multiple choices, and then this is like the percentage of like getting the right answer of the multiple choice.
No, so they're not all multiple choice. Many of them are open-ended.
But like so like the score is that is it like answer, so will the answer like correspond word by word, like sentence by sentence, or like is the like the general meaning correspond? If the general meaning corresponds, then like we will say like these two sentences like is a 1, or like how is this being defined?
So this is we only extract the answer part. So each benchmark like has a instruction at the beginning, like telling the model to provide the reasoning, and then answer by saying the answer is, and then the answer basically. So we have a regular expression that extracts the answer, and then from that answer we do a string match character by character basically to make sure that it's the same.
Sorry. So like what is the answer like? So you said the answer is like blank. So what is this blank? Like usually, and why like character by character at the end is the correct way of doing it? I didn't get it.
I mean, alternatively, people used to do like they used to use some metrics like the blur or rouge score or so on. But those are those are not like. I mean, we kind of like shows the more robust, more stringent approach of deciding whether the answer is exactly the same as the ground truth or not. There are other ways of measuring it, but for mathematical stuff in general and for other stuff, people usually measure the exact match, whether the predicted answer is exactly the same or not.
Okay, thank you.
Okay, so we also tried different post-training paradigms. So we tried something called DPO, which is called direct preference optimization. I won't go into the details of DPO, but it's just another way of like fine-tuning the model. We did see some mixed results for no experts versus specialized. But yeah, this is kind of was an interesting experiment to try. We also tried a different instruction tuning dataset, which is called like a medical one instead of Tulu, just to see if our model, our experiments are robust across different datasets and is not specific to Tulu, for example. Like this is only the stage 3, basically the stage 3 part. We just change the dataset to another dataset. And the case here that we found that in the out of distribution setting, the model is actually much better in two of the benchmarks, whereas the in distribution were better in some cases and in some cases not. But the out of distribution is usually what people care about, and yeah, it was it's good that the specialized model is able to perform better in this case.
There is a question in the chat. How do you calculate similarity measure when the answer is like an open answer? So exact match maybe is not the perfect metric for such a case.
Yes, I agree. So yeah, I think in some cases, so in general, like we do give like if the answer is not is like if there's multiple choice, we usually give the options, and then the model should be able to answer one of the options, and then we do exact match there. Like that's okay, I think. For open-ended, if it's not a number, I think usually all the open-ended ones we use here are numbers, if I remember correctly. The other ones had multiple choice.
But in empathy, for example, it's also multiple choice data set, or
Which one?
the empathy one where you
The empathy one. The empathy one. So the empathy one, we mostly use it for interpreting routing patterns because it was yeah, it was multiple choice actually. There was the ground truth labels were like when I investigated myself were not as good or not as not like I didn't find them reliable, so I kind of like didn't include them in the table. But like for the routing patterns, it kind of is where I chose them, where I only included the empathy benchmark. But here, yeah, again, like I think all the others are multiple choice, and only the mathematical ones are usually open ended.
so for the experiment with different experts, you only use multiple choice data sets to use this to calculate this metric. You didn't use something like Beard score or something like this for open-ended question.
No, I didn't use all of them are exact match.
Got it. Thank you.
So also, yeah, I mean, one of the reasons like people use exact match, and I use exact match in this case, is that it's kind of like allowing the model to follow to measure if it follows the instruction properly or not. Because if you have the instruction saying to the model you should output the answer in this format, and those are the options, you should only select one of those options. So it's kind of like as well seeing how the model is good, like if it's good enough to be able to follow the instruction or not. It's debatable whether that's the best approach or not, but like this is generally what we did. Okay. Yeah, I mean, okay, so steering behavior. So yeah, we tried ablating some experts. So by ablating, I mean we remove one of the experts and measure the performance before removal and after removal. And here in this case, we on the y-axis we report the difference, so the delta between the exact match. And for example, on the math benchmark, we saw that if we remove the logic expert, the performance will drop a lot. If we remove the social expert, the performance will increase, which was quite surprising as well. And the world expert didn't matter that much. So yeah, again, kind of confirming our expectation. For GSMAK, kind of the same. Like if we remove the logic expert, the performance will drop by a lot. Removing the social expert will increase as well, and the world expert will decrease by a bit. So, and for so on, and we did the same for MMLU. We kind of divided MMLU into different, in each subtask in MMLU into different categories. So into logic, social, and world, because like MMLU is a bunch of subtasks together, and our expectation is the same. Removing the relevant expert drops performance. Removing irrelevant one, usually it depends like on what exactly. And we did the same for BBH. Not all subtasks are clean as the other ones, but again, it's kind of like showing that the behavior can be steered by the ablation. And this is one funny example when I was trying out the model. So just to read it quickly, this is a prompt given to the model, like John is thinking about Mary, but he doesn't know if she likes him back. he's confused and anxious about the relationship. What advice can you give him to feel better? Can he give himself to feel better? So if you have the social expert in the model, it's going to give a very social response. So like John can give himself advice to feel better by practicing self-care, seeking support from friends and family, engage in activity that bring him joy and relaxation, blah, blah, blah. And then if you remove the social expert, the model is going to give a very logical response. It's going to tell it, take a deep breath and focus on the present moment. You can't control what Mary thinks about you, but you can control how you feel about yourself, etc. Like it's kind of like a bit funny, like how each expert is kind of like, again, like is important in allowing the response to reflect what the function of that expert is. Yeah, and last thing I want to present with the results is the neuroscience localizers. But first, let me know if you have any questions before I move on.
Yeah, sorry. How do you exactly remove an expert there? So you just state to the router that you do not route anything towards this particular MLP, or?
Yes, exactly.
Oh, that's simple. Okay.
So just I mean the router weights, I just set negative infinity to the logits and then do softmax.
Got it. Thanks.
Yeah. Okay. So neuroscience localizers. So just to give you an idea, so what are neuroscience localizers in the first place? So if you remember the language network, which we discussed before, so the language network in the brain is usually different from one individual to the next. So like the exact location is not in exactly the same place. So what people do, or neuroscientists do to identify where it is, they run a localizer experiment. So a localizer experiment is when you pass a set of, like for language, you pass a set of sentences and a set of non-words. And non-words is basically like, yes, it's words that doesn't make any sense. And a sentence is just a coherent sentence. So you pass both to the model, you extract all the activations, and then you select the activations that are most selective to sentences as compared to non-words. Usually we do this using a t-test. And the main idea here that we want to see whether if you use this localizer and other localizers, whether those localizers can automatically identify which expert is which one, only using neuroscience localizers. And that's actually what we found. So to give you, to walk you through this, like if you look at only the language, like the first one, language localizer, you have on the y-axis the depth. So we have here 16 layers. And on the x-axis, we have the language expert, the logic expert, the social expert, and the word expert. So as you can see, like most of the activations that the language localizer localize is in the language expert for Olmo and Llama. For the multiple demand localizer or the logic expert, it automatically identified the logic expert. But for the theory of mind localizer, it wasn't able to identify the social expert. And this might be due to the expert itself is not as robust or as good in theory of mind, or it's mostly because it's the localizer itself is not good enough. But that was a very cool result that we were able to show that if you select the same localizers that people use in neuroscience to identify those networks in the brain, they kind of like rediscover the experts in the model. So I found that pretty cool. And here the percentage is basically identify like how many how many units in this layer are part of the top one language expert. You have any questions about this? I know, like I have said a lot in those 2 slides.
Just maybe to understand whether we understood. So do I understand correctly that for brain there is a thing where you can identify like which region is used for the given prompt, like for logic for something else and you do it via some statistic test, like t-test you mentioned. And then you said, okay, instead of router, let's try to use again some sort of statistic and to try to match it again with the model, like to try to identify whether this is a logic expert or something else using the same t-test, or it's incorrect.
Yeah, so we use the same input or the same prompt that people give to humans when they try to, like, for example, they're in an fMRI machine, they're recording their brain activity, and then they try to localize where the language area is. And they do this by like making them listen to or read sentences and non-words. So this part basically. And the main idea here, then you kind of like the neurons in the brain that fire more for sentences compared to non-words are defined as the language area, are as part of the language area. And we do this, the same exact thing, we repeat it in the model. We give the same sentences and non-words to the model, like what's shown here basically. We identify which units in the model have the highest activation, and then we contrast both and select the one that are highest for sentences and are not highest for non-words.
Again, so here, where do we take these activations from? From each of the experts, or?
Yes, exactly. So we take activations from each of the experts. So here in this case, we have the 4 experts in the 16 layers, like in each layer basically. And we take activations from each expert, and then we find that the language expert has activations that are most selective to language.
So at the
compared to-
baseline, we do not know which expert is which. We just have a few LMPs, and then by this we okay, that makes sense. Thanks.
Yeah, exactly. So in the brain, we don't have we usually neuroscientists like kind of try to discover the brain, right? So we don't know which areas are responsible for what. So that's why they developed this methodology to be able to identify which areas in the brain are functionally responsible for. They do a lot of other experiments, but this is the main idea. And now we asked ourselves, can those methods rediscover the experts without having any knowledge about the experts? And that's what happened, except for the social one. And the reason we didn't do the world one is the default mode network doesn't have a linguistic localizer, as far as I know. But so we use the localizers that exist for language, basically.
I think it's clear now. Thank you.
Sorry.
Okay, perfect. Yeah.
So out router and the MOP where? What output will be?
Sorry, I can't hear you well.
Sorry, what output will be after each router and MOP where?
Which output? So here we take the output after the MLP, and this is the activations we select to know if how selective this expert is, basically. Is that your question?
Yes. Okay.
Okay.
Sorry, after MOP where, so after router layer, we'll have a distribution, yes? And what will be output after MLP layer to go to the next router, next layer?
So the output of, so we have the representation is given to the MLP, and then the router kind of weights according to the output distribution. Okay, I mean, let's say in my case, for example, in this paper's case, we select only the top one, right? So it's just like the router only decides which expert it should route to, and the token is only routed to that MLP, and then the representation is extracted from that MLP. And then this is passed to the next layer.
Yes, okay, thank you.
Okay. Okay, so concerning next steps about this project, is stuff that people might like basically naturally ask about this paper is we're planning on evaluating this on like behavioral benchmarks. Behavioral benchmarks as in like basically compared to human performance. So not only can it get like stuff that human gets right, but also get stuff that human gets also like get stuff wrong on stuff that human gets wrong. So make the same mistakes as humans. We also wanted to measure the neural alignment. So how similar their presentations are of each expert to the corresponding brain network. We want to try to scale it up. So basically we tried like 1 billion or 1.5 billion. Now, whether the results will hold in a much larger scale. And finally, like making the model multimodal, so make it work with vision input, auditory input, and so on. Yeah, and oh, sorry, no, where's the? That's weird. Oh yeah, there's this. Okay, so yeah, in general, there's a project page which includes the link for the paper, the link for the code on GitHub, and the link for the models on Hugging Face, so you can play with it yourself. You can look at their outer weights. You can try to ablate an expert and see how the generation changes, and all of that are like examples in the GitHub. And usually, if you want to follow me on Twitter, I'm active there and usually put stuff about my latest research. Yeah, and with that, I thank you for listening.